is Shanice Abraham, and this is my lab report on projectile motion. In this lab, our goal was to study the motion of an object and compare its real-world trajectory to a computational model with and without drag force. Before discussing the experiment, let's review key physics principles. Projectile motion can be explained using Newton's second law and the momentum principle. Without air resistance, the only force acting on a projectile is gravity, producing a uniform downward acceleration of 9.8 meters per second squared. However, in real life, projectiles experience drag, a resistive force that opposes motion. Drag is proportional to velocity squared. In our experiment, we discovered that the drag-free model matched our tracker data more closely, suggesting that the crumpled paper ball experienced very little measurable drag. For our experiment, we used a small crumpled paper ball with a mass of about 0.005 kilograms. We recorded its motion with a stationary camera, and we placed a meter stick in the frame as a scale reference. The system was the paper ball, while the surroundings included gravity and air resistance. We imported the video into the tracker software and tracked the position of the paper ball frame by frame. Tracker generated data tables and graphs for the ball's trajectory in both the x and y directions. From this data, we extracted the initial conditions, including the starting position and the velocity components in the x and y direction. We then added these values into the starter code in VBPython. The code was based on the momentum principle. We also updated the velocity and position over small time steps through here. To model drag, we modified the net force equation to include the drag term, which we represented as B. Here are our graphs comparing the tracker data with the computational model. The drag-free model matched the tracker data very well. When we added drag, the model trajectory shifted and no longer fit. We attempted drag values smaller than 0.1, but the program created them as nearly zero. At b equals 0.1, the drag effect was visible but unrealistic compared to our data. This suggests that the drag was negligible for our tightly crumpled paper ball. Some possible sources of error include the paper ball may have been thrown too forcefully, which can reduce drag effects, or the ball may have been crumpled too tightly, which decreases the surface area and air resistance. So to answer these questions, terminal velocity occurs when drag balances gravity so that the net force is zero. Our graphs did not show terminal velocity in the y direction because the fall distance was too short. In the x direction, velocity appeared nearly constant, but this just means drag was too small to detect. A better experiment to measure terminal velocity would be to drop the ball from a much greater height or use a less dense object. So to answer the second question, if the object had been thrown straight up, the total time would have actually been longer because the ball would first travel upward, slow down to zero velocity, and then fall back down. So the t total will equal the time up and the time down, where t up equals the initial velocity divided by gravity and t down, and which depends on the added height. This means it would take more time compared to the angle thrown in our experiment. In conclusion, this lab demonstrated the physics of projectile motion and how drag can be modeled computationally. Our results show that the crumpled paper ball experienced little measurable drag, so the drag-free model matched the experimental data best. This experiment highlighted how important initial conditions, object properties, and accurate measurements are when modeling real-world motion. Thank you for listening.